Hello and welcome to this CSTM Special Symposium. Today, we're welcoming people, attendees from right across the country and also the United States. We hope everyone is okay and surviving all of this business, and that we'll provide you with some entertainment over the next hour and a half that may actually be of some value to you. Next slide, Luca, please. And next one, please. A few housekeeping things. Please familiar yourself with the site interface. We will take questions and answers, but we're going to answer them and address them after each speaker's session. So please use the Q&A function to submit those questions. And remember, please, to complete the webinar evaluation survey at the end of this exercise. Your web interface will look something like this. The presentation will be where it's denoted here. If you encounter any issues, please do contact a panelist and use the chat function to do that. Speaker camera output will appear on the right side. When you submit questions, please do click on the Q&A button at the bottom of your screen to ask a question. Again, these will be addressed at the end of each speaker session. Submit a question anytime by typing in the box you'll see in the pop-up, and speakers will address those questions after their sessions. Next slide, please. During the course of this, of today's entertainment, you'll have opportunity to interact. And one of those mechanisms will be through a poll, and you see now on your screen a test poll, and you are welcome to answer this question as a practice exercise. Right, so we have two excellent guests with us today. Probably the two biggest experts in IG-associated hemolysis in the country, if not on the planet. We're very thankful to Drs. Pendergrast and Branch for taking the time to educate us here today. We have a couple of objectives over the next hour and a half. Those are to deepen our understanding of the incidence and the risk factors for IVIG-associated hemolysis, and also to explore new advances in prevention and minimization, if that is indeed possible. So IVIG, what is it? For those of you who don't know, it is made from donated plasma, and it can take anywhere from 15,000 up to even 40,000 donations to make one single lot of an IG product, and a lot may be as small as 26 kilograms. The idea is that there is a mix of broad spectrum of IgG antibodies in the products that protect the recipients against all kinds of nasty organisms that one would find in day-to-day life, used initially and pioneered initially as replacement therapy in immunodeficiency disease, but latterly being used as an immunomodulatory agent or an anti-inflammatory in a range of autoimmune diseases. Initially, this type of technology was developed at Harvard University by a fellow named Cohn, C-O-H-N, and he used cold ethanol at various concentrations to precipitate out different types of globulins. This was the foundational technology. Since that time, there have been improvements in manufacturing processes to improve purity and to increase yield. Those include octanoic acid or caprolate chromatography, polyethylene glycol precipitation. There are a number of different technologies that different manufacturers use. But an unhappy side effect of this improvement in manufacturing over the years has been an adverse event we know as IVIG-associated hemolysis, or intravenous immunoglobulin-associated hemolysis, and that's the topic of today's talk. So first of all, I'll introduce Dr. Pendergrast just very briefly. originally from Dalhousie. So with salt water in his veins, he's automatically makes him a good human being in my estimate, but I'm biased being from Newfoundland. He went to University of Toronto subsequently and now is an associate medical director at the UHN. And he has been seeing patients in the TGH with rare blood disorders since 2004. Dr. Don Branch is a very special and interesting fellow who, amongst other things, cut an album in his youth in California that was produced by George Martin. And yes, it is that George Martin, the same guy who produced the Beatles. And that's a pretty cool thing in my estimate. At any rate, Don is a real globally known expert in this space. He's advised the FDA on IVIG-associated hemolysis. He's developed a validated assay called the monocyte monolayer assay that he's published on extensively, which is able to predict hemolytic tendency. And he's been with Canadian Blood Services for quite some time. As a matter of fact, started his career in Edmonton, where he joined the Red Cross, and that was in 1985, I believe, if I've got my numbers right. So welcome to all of you folks once again. We're going to talk about hemolysis and two fine experts to help us to understand that. And so over to you, Dr. Pendergrast.
All right, thanks so much, Don. Appreciate that. So yeah, we're going to be talking a little bit about this phenomenon that I think a lot of us have encountered intermittently, maybe with increasing frequency over the past few years, whereby a patient gets treated with IVIG and then their hemoglobin drops and they show signs of hemolysis. And I think, you know, one of the questions we struggle with, you know, as medical directors of blood banks, as technologists in blood banks who investigate these patients, and as the prescribing physician at the IVIG, is why did this happen? Why this particular patient? So that's some of what I'll be going into for this presentation. And next slide. So we will start with a poll. In your current role, have you ever been involved in a case of IVIG-associated hemolysis? And I'm going to click my own poll. Okay, so it looks like just over half of the audience has been involved in a case. And I do know as well from the polling that we did before the start of this presentation that a lot of us, even if we haven't seen it, have certainly heard of it. And there's varying degrees of familiarity with that phenomenon. Okay, next slide. Okay, so we'll be going over what we know so far about the epidemiology and risk factor for IVIG-associated hemolysis. Next slide. For disclosures, I'll be talking about some research which was funded by Grifols and Canadian Blood Services. Next slide. Okay, so one of the questions that has come up when we sort of ask, why did this patient hemolyze after getting IVIG, was there something about that patient that predisposed them to that adverse reaction? You know, that affected that patient and not that other patient. And one of the questions or hypotheses that has been put out there is that maybe it is that these patients are inflamed at baseline. And this is why they hemolyze. It's the really sick patients who hemolyze. And it would make sense in a way, because we have known for some time that monocytes or macrophages, if you expose them to IgG opsonized red cells, and this is in a completely sterile environment without any involvement of the adaptive immune system like B cells or C cells, no dendritic cells with antigen presentation, just straight out IgG opsonized red cells, that when monocytes encounter those, they become inflamed and they start secreting inflammatory cytokines, IL-1 beta, IL-1 receptor agonist, that sort of thing, and then eat that red cell. They just, as you know, the process called erythrophagocytosis, and it was also shown in this early study that you could prevent this from happening if you blocked the high affinity IgG receptors on those monocytes. So I think this gives us a bit of a clue maybe as to what might be selecting out certain patients to get this reaction of IVIG-mediated hemolysis. Next slide. So in terms of how that might occur, the mechanism of inflammation is just quite complex, and this is greatly simplifying it. But one possibility is that patients who develop IVIG-mediated hemolysis have a skewed immune response towards what we would call a Th1 immune response, which is sort of that inflammatory pathway, which might serve to sort of prime their macrophages so that they are more likely to eat those red cells up. So in terms of what would skew you there, so various things that would skew you towards Th1 immune response, and therefore an M1 macrophage phenotype, would be things like an underlying infection, either with a virus, which would result in secretion of interferon, or to bacteria, which have things like lipopolysaccharide, which can bind to toll-like receptors on the macrophage. And then once you have done this, you will promote that macrophage and that M1 phenotype to have increased FcR1 high affinity IgG receptor expression. And then that monocyte will, once it has eaten the red cell, then begin secreting various inflammatory markers that you can then measure, things like increased C3, C4, fibrinogen, haptoglobin, ferritin, C-reactive protein, and so on, and then the various sort of symptomatic markers of inflammation. It's also possible, however, that you could increase a risk of hemolysis by having an M2 phenotype, which is sort of more of that kind of tidying up, cleaning up macrophage, which is involved in wound healing, angiogenesis, and that sort of thing. And the reason that might be possible is that we know that there are certain Fc receptors that are expressed on that sort of M2 monocyte, which are involved in clearing red cells that are opsonized in the setting of autoimmune hemolytic anemia. And so maybe IVIG is sort of, a predisposition to sort of an autoimmune hemolytic anemia type process. So we don't know. But these are sort of ways in which underlying inflammation could predispose you. And when we look at sort of evidence that inflammation predisposes you to IVIG-mediated hemolysis, next slide. We get case series such as this. So this came out in 2008, and it was out of Ottawa, and they had started to see quite a lot of cases of IVIG-mediated hemolysis, and they started gathering them all up, and they had a case series of 16 patients here, and these are sort of summarizing their demographics, what their diagnosis was, the dose of IVIG, what their blood group was, what the direct antiglobulin test results showed, what was eluted off the red cells after the IVIG was given, and the number of inflammatory markers that these patients had accompanying the hemolysis. For example, haptoglobin, ferritin, fibrinogen, D-dimer, and so on, as you can see at the bottom of the slide here. Next slide. So they found, looking at all this, that if they were looking for certain characteristics that were present in the majority of cases, a few things stood out. First of all, the patients who hemolyzed all seemed to be getting high doses of IVIG. They didn't quantify it in terms of weight adjusted, but certainly 100 grams over 2 to 4 days is what you would expect to give somebody getting an immunomodulatory dose. Almost all of these patients were non-O blood group, which just suggests a skewing, right? Because we know that group O is maybe like half of the population. Female patients seem to be at higher risk, which is interesting. And they also noted that a lot of them had inflammatory markers. But there were some other kind of other confusing or maybe difficult to explain observations that came along with this. One is that the fall in hemoglobin seemed to occur over this wide range of time. Sometimes it seemed to happen immediately after the IVIG was given, which would suggest that it was a complement-mediated form of hemolysis, because generally speaking, only complement can cause lysis that fast. But in other cases, it was 10 days later. And in a lot of cases, it was actually difficult to tease out how bad the fall in hemoglobin was due to the hemolysis versus some underlying comorbidity. Some of these patients were bleeding at the time, for example. So like in a third of the cases, it was hard to say, like, you know, was this actually due to the IVIG? How much did the IVIG actually contribute to the fall in hemoglobin? It's hard to say. So we, you know, from this kind of data, we had some clues as to who the patients at risk were. But it was a single arm study, and it was retrospective. So we're limited a little bit in drawing too many conclusions. Nonetheless, next slide. From that study, and from other studies that were coming out as well, and other case reports and case series, there was this two-hit model of IVIG-mediated hemolysis, which has been proposed, and which many of you may be familiar with. And so in this two-hit model, you are at risk of hemolyzing if you are getting a high dose of IVIG. Typically that means an immunomodulatory dose, not a replacement dose. And if you have underlying inflammation. They also included HLA sensitization as a possible risk factor as well, if you had a lot of anti-HLA antibodies. The mechanism for that was thought to be immune complex formation, you know, and maybe that was in turn sort of triggering more of that kind of M2 monocyte phenotype with sort of that sort of wound healing kind of function that we talked about before. We don't know. But in any case, once you are hemolyzing, the mechanism appeared to be it was binding of anti-A and anti-B isoglutamins in the IVIG to the red blood cells, which are then either cleared by splenic macrophages or lysed intravascularly due to complement activation. So that's the kind of the model that was put forward. But again, this was sort of more hypothesized. We didn't really have proof. This would sort of fit what we were seeing, but it didn't necessarily have a definitive data set to support it. It was mostly just sort of retrospective case series. All right, so we'll go to a poll next. All right, so based on your understanding of IVIG-mediated hemolysis, which of these factors influence a patient's hemolysis risk? And you can select more than one. Is it the patient's ABO blood group, their age, the indication for IVIG treatment, the dose that they got, or the presence of an underlying inflammatory state or systemic inflammation? Okay, so looks like most people are fairly convinced that it is the blood group and the dose of IVIG. A number of people are also fairly convinced by the data so far that patients who have an underlying inflammatory state are also at greater risk. The age of the patient and the indication for treatment doesn't seem to be as important. Okay, next slide. So to really answer this question, to really tease out how often does this occur, who does it occur in, and how does it occur, you really need to do a prospective observational study, which means that you enroll your patient before they get their IVIG, you get some baseline tests performed, you give them their IVIG, and then you see what happens. That's probably the best way that you can tease out who is hemolyzing and who is not, and why. So in this study, we wanted to look only at patients who were not blood group O. We wanted only to include patients who were getting high dose IVIG, defined as a cumulative dose of 2 grams per kilogram, adjusted for ideal body weight over a 28-day period. And then we wanted to have a standard battery of tests. We wanted to look for signs of hemolysis. We wanted to check all their DATs, check their complement levels, their ferritin, perform a monocyte monolayer assay or test to see if we could replicate in vitro the type of hemolysis we were seeing in vivo. And then we wanted to collect this huge panel of additional referral or extended tests to see if we could pick out other risk factors. So aviozygosity was one question. You know, does it have to do with the density of A or B antigen expression on your red cell? Secretor status we thought might be important. Maybe if you have soluble A or soluble B and carbohydrate in your plasma, you can kind of mop up the excess anti-A or anti-B that's in the IVIG and protect yourself. Were certain polymorphisms in your IgG receptors responsible for why some patients hemolyzed and others didn't? And then we did this cytokine profile panel looking to see if there were certain markers of underlying inflammation which would identify a patient who is at risk. And so we did this by drawing all these lab tests immediately before the IVIG was given, within 24 hours of the IVIG, and then we had the patients come back 5 to 10 days later for one final set of labs, just to make sure we could catch any sort of delayed onset IVIG. Okay, so that was our protocol. Next slide. So it was a complicated protocol to operationalize. To really get enough patients, we had to recruit from a large number of hospitals, because we were restricting ourselves, remember, to high dose IVIG to non-O recipients. And we wanted to make sure we had some pediatric patients as well. So we got some from sick kids. We collected all these samples. We did a lot of testing in the hospital, and then we would send samples to Don Branch's lab, where he would perform a monocyte monolayer assay. And then he in turn referred samples out for all sorts of extended testing. We were looking for aviozygosity secretor status, FCR polymorphisms, IgG subclasses in the eluate, cytokine panels that we performed in a variety of different labs that were available to us. So it was a challenging protocol to implement. But I think it was worth it because we had some really kind of interesting results. But before I get into that, I'll also just go into, next slide here, what the definition of hemolysis that we followed were. And this is important because, you know, we know that if you give somebody, you know, a liter or two of any fluid, IVIG or otherwise, their hemoglobin will go down. It'll be a dilutional effect. So to really prove that it was IVIG mediated hemolysis, we followed the standard definition developed by a pharmacovigilance group set up by the Public Health Agency of Canada, whereby we said you could only call it IVIG mediated hemolysis if you had a positive direct antiglobulin test or something that you could pick up in the eluate right after the IVIG was given. And you had to have at least 2 hemolytic markers. And because we were having baseline samples drawn before we gave the IVIG, we could be quite particular about this and say, it wasn't just a matter to say that your reticulocyte count was elevated, it had to be elevated from baseline. So high elevation in your retic count, your LDH, your bilirubin, or a fall in your haptoglobin. You had to have at least 2 of those things. The grading of hemolysis, again, was a standard definition set up by the Canadian IVIG hemolysis pharmacovigilance group, whereby grade 0 meant that you had compensated hemolysis, that your hemoglobin didn't fall, even if you were, you know, having a spike in your bilirubin and LDH. If your reticulocyte count could keep up, it was grade 0. And then grade 1 was if your hemoglobin fell from 10 to 20. Grade 2, again, it was stratified based on what your starting hemoglobin was, all the way down to grade 5, which was a fall in hemoglobin that was so severe that it resulted in organ failure or death as a direct consequence of hemolysis and anemia. So this is the outcome measures we were looking for this study. Okay, so next slide. In the end, we captured 99 infusions of high-dose IVIG to 78 non-group O patients. And this study was conducted between 2013 and 2016, so it reflects, you know, the risk of hemolysis with the products available at that time. We were able to perform extended cytokine panel testing for 54 of those 99 infusions, monocyte monolayer assay testing on 50 of them, and then we had PCR studies for abiozygosity, secretor status, and FCR polymorphisms in 37 of those patients. Of those 78 patients, 56% were female. Mean age was about 49 years old, although there was quite a range. We did have some pediatric patients as well as some fairly elderly patients. BMI was average, I would say. Most of these patients, reflecting the fact that they were getting immunomodulatory disease, were being treated for neurologic conditions. 60% of them had been treated with IVIG in the past. Immunosuppressants were being given to 31.3%. This included things like azathioprine, MMF, cyclosporin, that sort of thing. Just under half patients were given steroids, and then a smaller percentage were given steroids as pre-medication just before the IVIG. The mean weight-adjusted dose, again adjusting for lean body mass, was about 2 grams per kilogram. Most patients got that whole dose over around 2 days. Some patients had it over longer periods, like 5 days. Some were getting it even every 2 weeks, but most of them were given it over a couple of days. And the mean infusion speed was basically as per manufacturer recommendations. Next slide. You can see again that most of the patients had neurologic conditions, including this large swath at the bottom here of other diagnoses. Most of these were also various neurologic conditions as well. But we had some other things as well. We had some patients who were being treated for solid organ transplant rejection, Kawasaki's disease, ITP was a very common indication. Next slide. We started recruiting a little slowly because we started just at the University Health Network in Toronto. It picked up a little bit in 2015 when we started recruiting from other hospital sites as well. Because we had allowed patients to be re-enrolled a maximum of 6 times, by 2016 we were starting to run out of patients that we could enroll. And that's when we started analyzing our data. Next slide. The products we provided reflected basically what Canadian Blood Services provided to the hospitals, and it was sort of in keeping with their supply chain. So most patients were getting treated with Grifols products, some were getting treated with CSL Behring products. Octapharma was the product given preferentially to one particular hospital, as it turned out. Most patients only got one manufacturer for their course of therapy. There were a few who had a mixture, like they would come in one day and get one product, the next day they'd get a different brand. Next slide. And what we found, and this was quite surprising actually, was that hemolysis was much more common than we thought. The traditional teaching about IVIG-mediated hemolysis is that this is a rare complication. Like people quote, like maybe 1% of cases will cause hemolysis. It's considered to be kind of like that's sort of a slightly esoteric type of reaction. What we saw actually fit what was happening in the transfusion medicine community in Canada and around the world, which is that we were seeing more and more of these cases. And some of it had to do with the fact, certainly, that you have to look for it to see it. But when you do look for it, as we were looking for it, it's quite common. So 1/3 of cases, and again, these are just high-dose IVIG given to non-Group O recipients, 1/3 of cases showed signs of hemolysis. Sometimes it was quite mild, you know, but sometimes it was grade 0, compensated at grade 1, so the hemoglobin would fall like maybe 10 grams per liter, not a big deal. But some of them were fairly severe. We didn't have anyone develop organ failure or death, but of the patients who developed hemolysis, about 1/5 of those had grade 4 hemolysis, meaning a very significant fall in their hemoglobin, like 40 grams per liter or higher. And you know, some of these patients required hospital admission and transfusion support. So it was not a rare complication in the end. Next slide. This is where it starts to get really interesting when you start comparing the kinetics of hemolysis between the patients who actually did hemolyze and those who did not. So starting with the proportion of patients who had a positive DAT immediately after the IVIG was given. By definition, all our patients pretty much had a positive DAT right after the IVIG was given if they went on to develop hemolysis. The few patients who hemolyzed who had a negative DAT met the criteria because we did an eluate study because we were so suspicious, and sure enough, we found an anti-A and an anti-B. But you'll also find that amongst patients who didn't hemolyze, almost half of those patients still had a positive DAT. So having a positive DAT after you get IVIG does not mean you're going to hemolyze. It turns out that if you have a strongly positive DAT, like 1+ or stronger, that seems to select out a little bit more. That seems to increase your risk of having hemolysis. But again, it's not a guarantee. You know, 23% of patients who did not hemolyze still had a 1+ or stronger DAT. What's further interesting is that by the time we did that final investigation at day 5 to 10, fewer patients still had a positive DAT. It was 38% amongst people who hemolyzed versus 19% amongst those who didn't. And what makes this particularly slippery as a diagnosis is that although the immediate fall in hemoglobin between those who hemolyzed and those who didn't hemolyze was very similar, you know, indicating that at least some of this was just a dilutional effect. It was only when they came back at 5 to 10 days later that you really saw the difference in the fall in hemoglobin. So when they came back 5 to 10 days later, the patients who hemolyzed had an average fall in their hemoglobin compared to pre-IVIG of 23 grams per liter. But at that point, many of them no longer had a positive DAT, presumably because the opsonized red cells had been cleared. However, it was also at that final blood work that they actually had the increase in their LDH and their bilirubin. So it's very tricky. You know, if you check a patient for hemolysis right after they get the IVIG, you will see the positive DAT. If you have them come back 5 to 10 days later, then you'll actually see the hemolysis, but very often the DAT is negative by that point. And I think this is why this diagnosis is so easy to miss, because it only meets that definitional criteria if you check it on 2 different occasions. It's also, I think, what this data shows, why IVIG hemolysis is so easy to overdiagnose, because most patients will have their hemoglobin fall when you get IVIG, whether you hemolyze or not. Most of that is dilutional. It's only later that the actual hemolysis kicks in. Also, interestingly here, we did not really see much evidence of complement consumption. Certainly nothing that distinguished the hemolyzers from the non-hemolyzers. And it was also worth noting that none of those positive DATs that we had were positive for complement. They were all just positive for IgG. We looked at the ferritin as sort of as a marker of macrophage activation, however, and sure enough, the ferritin did increase amongst those who hemolyzed. But again, you had to wait 5 to 10 days before you saw that proportional spike in the ferritin that distinguished the hemolyzers from the non-hemolyzers. Next slide. For the patients that we did the monocyte monolayer assay testing on, this was also an interesting finding. So what we did here is we collected monocytes on day 5 to 10. This is after the IVIG has been given. And then we showed those monocytes, the patient's own red cells. And we said, here are some red cells before you get the IVIG. Here are some red cells after the IVIG was given. And here are some red cells drawn at the same time that the monocytes were collected, which is day 5 to 10. And you can see that comparing the hemolyzers from the non-hemolyzers, there didn't seem to be much difference in phagocytosis when looking at the pre-transfusion red cells. It was only afterwards that we saw the spike. And that suggests that it was not the macrophages being inflamed at baseline. It was, in fact, the density of antigen or of IgG deposition on the red cell surface. Next slide. Group AB turned out to be a particularly high-risk group. Almost all group AB patients hemolyzed, whereas it was roughly a third of patients who were group A or group B. Next slide. Antigen density appeared to be important. Patients who were group O heterozygotes appeared to have a trend towards lower risk of IVIG. If you had less antigen density, then you had less hemolysis. Next slide. Patients who were group A2 Heterozygotes also were at lower risk, again, showing that antigen density on the red cell was important. Next slide. Patients who had been treated with IVIG in the past appeared to be at lower risk of hemolysis. It was the first time recipients who seemed to be at higher risk. Like 50% of those patients hemolyzed to some degree on their very first IVIG infusion, whereas only 20% amongst the IVIG veterans. Next slide. Being treated with immunosuppressants appeared to be protective. That shut down the risk of hemolysis from 41% to 12%. Oh, sorry, that's 13%. If you were concurrently being treated with things like azathioprine, MMF, cyclosporin, that sort of thing. Next slide. We did initially see signs of an increased risk of hemolysis in patients who were getting the CSL-bearing product compared to patients who got Grifols or Octapharma. But we think this is actually confounded because when you corrected for all these other risk factors, AVO group, immunosuppressant therapy, first-time IVIG therapy, at that point, the product effect did not seem to be significant anymore. So I think this is probably a chance finding. Next slide. We did not see any association between the risk of hemolysis in patient age, sex, BMI, their diagnosis, how many days they got the course over, the rate of infusion, the total dose. Remember, all these patients were getting high dose. Concurrent use of steroids, steroid pre-medication, FCR polymorphisms, secretor status, or the IgG subtype. Next slide. Again, just to go into details here, no significant difference by FCR polymorphism. Next slide. Secretor status, no significant difference in hemolysis risk. Next slide. Pretty much everybody had IgG2 eluted. Didn't seem to have any particular predisposition towards hemolyzers versus non-hemolyzers or severity of hemolysis. Next slide. So in conclusion, what we saw from the study is that if you take a non-Group O patient and you give them high-dose IVIG, you are quite likely going to see hemolysis. It's not all that rare. Usually it's mild, but you will see it if you look for it. We didn't see any particular relationship between product or lot number. What we did see, however, was that it really had to do with how densely opsonized the red cells were with isoglutamins. You could see that with a stronger DAT, and you could see it mechanistically because patients who had lower antigen expression on their red cells had lower risk. Secretor status, for whatever reason, didn't seem to protect you. The mechanism appeared to be erythrophagocytosis, not complement-mediated lysis. Next slide. And importantly, most of the time, the hemolysis was delayed in onset, and that probably indicates the fact that the IVIG was itself stunning the macrophages so that they couldn't respond to all these delicious opsonized red cells around them until the effect of the IVIG had begun to wear off, and then they made their move. So 5 to 10 days later was when the hemolysis occurred. The highest risk in the first-time recipients is possibly a selection bias. You know, the patients who had bad reactions to IVIG might have been taken off it, but it could also have been the fact that the immunosuppressant effects of the previously given IVIG were protective. Diagnosis, demographics like female sex, for example, did not seem to be significant. Brand and product dosage and rate of administration were also not significant. Next slide. Okay, so final poll. Which of the following patient-related risk factors for IVIG-associated hemolysis do you think, based on what I've shown you so far, is the most relevant to your clinical practice? AVO blood group, IVIG dose, concurrent immunosuppressive therapy, prior experience, or none of the above, and you can only pick one. Okay, interesting. So I think most people have recognized that the blood type is important. Now I should say we didn't enroll a lot of non-Group O patients. Although we did have a few when we started this, and we did not see a lot of hemolysis in those patients. So I would agree, ABO blood type is probably the most important consideration. In particular, if you are group AB, those are the ones you really have to look out for. The dose also appears to be quite important. Is it more important than your blood group? That's harder to say. That we did not tease out. But again, certainly you don't see hemolysis very often in patients who are getting the sort of supplemental dosing that you get to the hypoGAM patients. And then I guess people consider the other risk factors to be less important. Okay. That is the end of my presentation, and we can take some questions now.
Brilliant, brilliant, Jacob. Thank you very, very much. Very interesting stuff. A couple of quick questions, and we do have to scoot in the interest of time. First one, did patients who were DAT positive respond to IVIG versus DAT negative patients? This question is based on Salama, first proposed that IVIG worked by causing hemolysis, and this resulted in anti-D being used.
That is such a good question, and we did not ask that for this study. We did not follow up whether the patient's Guillain-Barré syndrome got better if they hemolyzed versus didn't get better. To really answer that, you would need to do a different kind of study. But I think it's a good question. But I think we all appreciate that the mechanism by which IVIG has its immunomodulatory effects is probably broader than just hemolysis.
Thank you. Second one, this will be it. Has hemolysis been seen with subcutaneous infusion of IgG?
I am not aware of a definitive case of subcutaneous IgG causing hemolysis. I may be wrong. There may be case reports out there. I would look at those case reports carefully, though, because, as I say, there are a lot of reasons that you could have a confounded answer to this, like a fall in hemoglobin and an increase in LDH after getting sub-Q IG is not itself necessarily indicative of hemolysis. But I'm not aware of that happening, no.
Okay, thanks very much. I do apologize for anyone who submitted a question that we weren't able to address because we are short on time. All questions will be addressed, is my understanding, so stay tuned. And now we're going to move on to Dr. Don Branch, who will talk about prevention and minimization of IVIG-associated hemolysis. Over to you, Don.
Can you hear me?
Yes, sir.
Okay. I don't know if I should talk about this topic or about my solo single record, but nonetheless, I will move on and we'll discuss this particular topic. Next slide, please. So this is the title of my talk, and just some pictures of red cells with antibodies, which I'm sure you're all familiar with, and then a macrophage eating a red cell, which is the electron micrograph. These are my disclosures. Next slide, please. Okay, so obviously we know that blood plasma is used for IVIG manufacturing, and it contains ABO isoglutenins. That was pretty clear from both David's introduction as well as Jacob's talk. The isoglutenins that are contained in IgG are responsible for the associated hemolysis. So you probably know that IVIG is made from, as David pointed out, thousands of donors. Up to really 60,000 donors can be used, even more sometimes. 75 to 80% of the plasma donors are going to be group O or group A. So what you're going to get in these plasma donations is a lot of anti-A, a lot of anti-B, and we can talk later about anti-A comma B and some others. So that's going to lead us into this discussion of what are ABO isoagglutinins. So the Nobel Prize in Physiology or Medicine 1930 was awarded to Karl Landsteiner. I'm sure you'd all love to have this guy as your boss. I mean, you'd hate to have him looking at you from across the street. Anyway, Landsteiner discovered the ABO system, and he was disappointed in getting the Nobel Prize for that because he thought his other discoveries were much more important. And he is the person who discovered and coined the word happen. So he showed that an individual can make antibodies to anything, and therefore the diversity of B cell antibody response in human beings. And he thought that would have been better Nobel than what he called stupid blood groups. Next. And this is all he did to get the Nobel Prize. This is not his work, but this is similar to what he did. Is he had 4 or 5 people in his lab, including himself. So he knew that blood transfusion was having a lot of issues. They were using animal blood pretty much to transfuse people, and they were dying on the gurney. And then when they tried human-to-human transfusions, a lot of people had problems. And he hypothesized that maybe humans had something in their blood that was different, and you might need to match this blood. So he just did a simple test. He took red cells and serum from 5 or 6 people in his lab, and he just mixed them on a tile. And he got different reactions, and he saw that there were different patterns in these reactions. So as you can see here, the serum typing in the top from different known now blood groups, and the RBC typing. In his day, he didn't know anything about what the red cells were or what the serum was. But because he saw patterns like the A, if you look at the right side, A there, you could see that with the serum, when he typed this particular patient or his lab mate, he saw reactions with 2 of the other sera from his lab. And this turned out to be one type that he saw. And then when you look at B, he saw a different pattern when he did this typing with his lab mates. And finally, a couple of years later, his postdocs did some other typings, and they found this AB pattern and then this 0 pattern in his lab. So he named them originally A, B, and C, which makes sense. So O was originally C. And then, as I said, AB was discovered a few years later. Next slide. Anyway, 1 Nobel Prize just for that. Okay, so this is basically the ABO system, a little bit of chemistry. The ABO antigens are carbohydrate, they're not protein. So what you want to look down here is at the lower right corner. This is sort of the precursor carbohydrate system for the ABO system. It's in a special blood group called Bombay, but basically they've got a carbohydrate pattern that has a galactose that is not fully sourced with another carbohydrate. And what happens is the carbohydrates are added by glycosyltransferases. Those are proteins, and they're on specific chromosomes. So anyway, these particular people that are Bombay lack a fucose glycosyltransferase, and they can't add that to the carbohydrate structure. But when they do add it, you get group O, which is to the left of the Bombay. So you can see the dark colored symbol there. That's a fucose. And when that's added to that particular galactose, you actually get a determinant called group O. And group O is about 1 million sites per cell. There's really no gene that does group O itself. So it's really just adding that fucose, and then you have a group O individual. However, if you look up to the right-hand corner, you see that if you add another carbohydrate with a different glycosyltransferase, you add a galactose to that group of fucose, galactose, and another galactose, you actually end up with group B. And that's about 7.5 times 10 to the 5th antigen sites per cell. And then if you just go to the left there, you see the A antigen. It's a different addition to the galactose and fucose. It's an N-acetylglucosamine, and it's in purple here. And when you have that added by a specific glycosyltransferase, you have group A, and that's about 1 million sites per cell. Next slide. So you see it's carbohydrate system. Now Bombay are interesting, and we'll talk a little bit about the problems with Bombay, but there's that little, what's called little h. And then you see that in the H antigen, this is group O, this would be a normal group O. They've added that specific fucose to the galactose there. Next slide. So Landsteiner, when he basically published that in a journal and finally won his Nobel Prize, he actually established something that's really unheard of in immunology, and that's the Landsteiner's rule. What is the Landsteiner's rule? Well, basically it says that if you're group A, so you see antigen A on there on the left that has 1 million antigen sites, every single individual who is group A makes an antibody to the antigen which he lacks. That's Landsteiner's rule. So if you're group A, you always have anti-B in your plasma. And because of that, if you look down at blood type, you are a type A. That's the whole definition of forward typing on the top, reverse typing in the antibody part. So you have a group A. You should confirm that. If you don't see that, you've got a problem. And when you find that, that's a type A. So type A's cannot be transfused with group B or AB blood because they have anti-A. If you look at group B, same thing. If you're a group B, you always have anti-A. That's Landsteiner's rule. And so a type B person cannot have A or AB blood, but can be transfused with B or O blood. If you're a type AB person, you have both antigens. And Landsteiner's rule, you have both antigens, you cannot now make any antibodies to ABO. And therefore you can have any type blood transfused and you are the universal recipient if you're an AB individual. If you're a group O, okay, Landsteiner's rule, what do you think? Well, you're group O, you have no A or B antigens. Well, now you have both anti-A and anti-B, and you can only be transfused with group O blood. And that's why group O blood is considered the universal donor, because as you can see across the board here, O can be used in all of these blood types. Next slide. Okay, so what are the ABO isoglutenins? Now, I'm sure you all know this, but obviously anti-A. Anti-A is found in blood group B, O, and Bombay individuals. You can also have an anti-A1. It's found in group A2 and group A2B individuals. And A2B, it often is about 25% found in A2B individuals. You can have anti-B. It's found in blood group A, O, and Bombay. You can have an antibody that isn't anti-A or anti-B, but it works with both antigens, and it's called anti-A comma B. It's found only in blood group O and Bombay individuals. And in Bombay only, you can find, why? Because of Landsteiner's rule, they don't have H, so you can find anti-H in Bombay individuals. So Landsteiner's rule is a hard, fast rule that basically is unheard of in immunology, because you guys all need a tetanus booster every once in a while. You don't need any boosters in Landsteiner's world, and nor do you need, are there any exceptions? In other words, there's no non-responders, which is unheard of. So the idea of how anti-A, anti-B, and all of these isoglutenins are produced is, I think, still controversial, but it may not be an adaptive immune mechanism. Next slide. Now, if we look at IVIG, again, I mentioned that, you know, you've got about 75% of your donors are going to be O or A, could even be higher than that. So you're going to have a lot of isoagglutinins in your fractions. But there are three different ways that IVIGs have been prepared over the years. One is the cone fractionation that David mentioned. Basically, what that did is it gave you a good IgG yield and quality, but the isoagglutinins, it gave you a low IgG yield, and the quality of the IgG wasn't as good as some people wanted, but it also gave you low isoagglutenin titers. So the estimated percent of overt hemolysis given cone fraction IVIG is probably close to 0, just because you don't really have very much isoagglutinins and your IgG is not as good a quality, or you don't have as much of it in that product. So manufacturers, because they were more concerned about the antibody levels for immunodeficiency, decided that they wanted to improve the yield of IgG and the quality of the IgG. So they switched to a chromatographic method, and basically they got what they wanted. They got lots of IgG and they got high quality IgG, but oops, they got huge isoagglutenin titers. And therefore they started getting estimated, or hemolysis. Now that 8% is estimated based on what people thought of before Dr. Pendergrast and my study, which is higher than 8%, but you got hemolysis with this product. And then they decided that anti-A, anti-B wasn't very good. So in addition to the chromatography-based approach, they decided to remove specifically the anti-A and anti-B with another called affinity chromatography method, so 2 chromatographic methods to get still the high yield IgG and quality, but now a low yield of isoagglutinin titers. So next slide. So the products that we're talking about are the chromatographic one versus the 2 chromatographic products. So basically that's reduced isoglutinins versus non-reduced isoagglutinins. So when you look at this slide here, this is just comparing in a paper that you can see the reference at the bottom where they were looking at titers of anti-A. Now the Carimune sandoglobulin on the right was sort of a gold standard because that was the old cone process. And this was the anti-A, anti-B titers that were in that, and they wanted to get close to that. So when you look at the titers that were in Privigen at the time, that's the product that's being reported in this. This is without the second chromatographic process. They were having titers of 16 and 8 for anti-A and anti-B. And when they put this product through the second chromatographic to reduce the isoagglutinins, then their titers were reduced considerably to 2 and 1, which was very comparable to the Carimune and sandoglobulin product. So this is the Privigen that is also considered isolow. Next product, or next slide, sorry. So how do we get hemolysis? Well, most people now would think that IgG doesn't really activate complement unless it's certain antibodies that have certain angstrom distance between each other. But normally you have 2 kinds of hemolysis. IVIG associated is extravascular. It shouldn't probably use complement activation, at least not for the isoagglutinins, because people have shown that IgG, anti-A or anti-B do not activate complement. So the findings from our study are actually consistent with the science that for whatever reason, these are not very good complement activating IgGs, and your intravascular hemolysis is due to the IgM component of anti-A, anti-B. And that's the danger signal when you're transfusing O, blood group A into a group O. It's the IgM component in the group O that's going to cause the intravascular hemolysis. But what does IgG do? Well, IgG binds to the red cells, as you see in the lower part, and it causes extravascular hemolysis. And that's due to interaction with macrophages in the spleen and liver that have FC receptors that see the FC portion of the immunoglobulin that's on the red cell and then bind to it and phagocytose it and destroy it. Now, this can be very rapid and cause significant and rapid downregulation of hemoglobin. And this has been shown with anti-D mediated hemolysis, which also is extravascular, doesn't bind complement, but you can have severe what appears to be intravascular hemolysis due to anti-D, and the same happens with anti-A, if depending on probably host factors as to whether or not the hemolysis is rapid when it's extravascular, but it can be very rapid, and you can actually get hemoglobinemia due to extravascular lysis. Next slide. So the question then becomes, can we assess this in vivo extravascular hemolysis using an in vitro method? So you all are probably, or most of you are familiar with the monocyte monolayer assay, that this was an in vitro assay of antibody-mediated phagocytosis that was developed in the early 1980s, and it mimics the FC receptor-mediated action of macrophages in the liver and the spleen. So it's an assay that's been used to actually predict whether or not you will have a hemolytic episode when you are going to transfuse donor cells that are antigen positive for antibodies that the patient has. And based on this in vitro assay, you can accurately predict what the outcome would be if you transfuse antigen positive blood into these individuals. So it's a good assay to look for and predicting hemolytic events in vivo, even though it's an in vitro assay. Next slide. I think we're going to have a, okay, no poll yet. Okay, so we're going to talk about monocyte macrophage phagocytosis for a minute. Next slide. So again, it's basically just whatever the particle is that the antibody binds to. So it's an IgG antibody. It could be a pathogen, or it can be a red cell or a platelet. But once the antibody binds to that target, It's recognized by Fc receptors, and these are gamma receptors because these are IgG antibodies that we're speaking of. And then once it's recognized, it sends a signal into the cell that causes it to be phagocytosed and destroyed. Next slide. So this is the in vitro monocyte assay. If you read this from left to right, we start by whole blood, obtaining whole blood. We then put that on a density gradient and we get some fractions that you can see. And it's the middle kind of fraction you see there that's labeled PM or PBMCs that we isolate because that contains the mononuclear cells that are T cells and B cells, but also monocytes. And we put those into chamber slides. And then we incubate that for an hour, and then we wash it, and that removes all the T and the B and all of the non-adherent cells, because the monocytes actually will adhere to these slides and stick down, so you can wash these slides and get rid of all the extraneous cells. You end up with about a 90% pure layer of monocytes, and then you can go ahead and take red cells and you can opsonize them with allo or autoantibodies or with IVIG. And you can then put them onto these chamber slides with the monocyte layer. And then you can look for phagocytosis. And you can see what a stain slide might look like, showing phagocytosed red cells. And then you go ahead and create a graph with a cutoff, which is normally anything greater than 5, which is that checkered line, is considered clinically significant. Anything below that would be considered clinically insignificant. And what it's showing here is an anti-YTA antibody, an anti-Cartwright, where you can see that all of these units that were Cartwright positive were incompatible. The Cartwright by indirect antiglobulin test from 2+, 1+, and you can see the YTA negative ones were negative, as you might expect. Those were rare donors. Anyway, this assay predicted that if you transfuse the antigen positive units, they would survive as well as the antigen negative units. And this was actually tested in a patient, and we were right, yay, knock on wood. But this assay has been known to predict this for quite a few years now, so we weren't surprised. So again, this is an assay that can accurately predict what happens in vivo, but in an in vitro assay. Cindy Tong actually worked on this assay quite a lot, so she's indicated there. Next slide. And this is what it looks like. We use, actually looks like under the microscope, we use phase contrast. And if you just look at the upper left corner, that's phagocytosed red cells, and that's what we're counting. So we count how many of those cells are in 100 monocytes. So if you just look at the one on the right there, 1, 2, 3, 4, 5, 6, that's 6 red cells in a monocyte. And then we count 100 monocytes and all the red cells, and then we come up with an index. And anything greater than 5, so you can already see we have greater than 5, that this would be a clinically significant antibody, even if we counted 50 other monocytes that had nothing in them. Next. So we wanted to investigate whether or not reduction of the anti-A and anti-B antibodies in the isoglutenin-reduced IVIG can significantly decrease phagocytosis. So perhaps we can go to a poll. I think it's next. And this poll. Okay, so the question here is, to what extent do you think reducing anti-A and anti-B antibodies in isoglutenin-reduced IVIG would be able to decrease phagocytosis? Not at all, slightly, less than half, about half, significantly, more than half, completely, or close to completely? And please answer now. All right, so most of you said significantly more than half. That's a good guess. I cheated, I know the answer. So we'll move on to the next slide and you'll see if you were right or not. Okay, so what we did is we obtained, I gotta get rid of that. We obtained iso-reduced and non-reduced materials from CSL Behring in Bern, Switzerland, where they provided us with quantified IVIG products where we knew the protein content, the anti-A, anti-B titers that were done by fluorescence actually, and the amount of total globulin in percentage. So again, the non-reduced product we got was 20% IVIG, so that's why you see the difference in numbers there. But they were both 99% IgG, and their titers were different because of the 20%. Partly because of the 20% difference, but also because of the non-reduced. So you can see the iso-reduced one was quite low, much lower than the non-reduced titers, but the titers were still there. So they still had anti-A, anti-B reactivity. Now, when we did serologic titration titers, we had to do this by total protein. So we calculate total protein and went ahead and did the titers. And what you see, obviously, is a much less titer in the reduced IVIG than in the non-reduced. So you can see that the titers in terms of mgs per mil, remember it's total protein, you can see that we're getting 2 mgs per mil reactive with the non-reduced for both A and AB cells, and for B cells about 4 mgs it took to get a reaction. But you can see in the iso-reduced, in B, we don't even get a reaction until we're up to 30 mgs per mil of total protein. And for the A, it takes about 10 mgs of total protein. So there's quite a difference in the titer based on the exact same amount of total protein. Next slide. So when we did a phagocytosis assay and did an actual dose response over a concentration range of these IVIGs, up to 50 mgs per mil, you can see that the top three, the green, the blue, and the black with their little circle in it, they're all clinically significant by phagocytosis assay, even at lower concentrations. So they're even down to 10 mgs per mil, they're giving us a greater than 5 phagocytic index. But you can see that the iso-reduced one, even at 50 mgs per mil, is still not really giving us a result that would say that it would be clinically significant if infused. Next slide. Now we looked at some different ways of looking at this, and this might be easier to see for the activity here. But this is just a normal MMA. There's no manipulation here. What we've done here is we've used the concentration based on total protein of both IVIGs, reduced and non-reduced, that is equivalent to 2 grams per kilo being infused into an individual. So as you can see here, whether we use A1, B, or AB cells, the non-reduced IVIG is giving us a highly clinically significant result. You would not want to transfuse this material into an individual who is probably group A1, B, or AB. On the other hand, iso-reduced IVIG doesn't hardly give us any phagocytosis at this level of equivalence to 2 grams per kilo IVIG infusion. So next slide. So maybe that's good, but how about if we activate these monocytes? You heard from Jacob about inflammation, and this might be something to consider. So we went ahead and activated the monocytes. Wow, only that, really? Okay. So anyway, go to the next slide. We've got to go through this quickly because obviously this is taking too long. We looked at M1, M2, still no difference. Next slide. Let's see if I can get through this in a minute. Next slide, we'll do this at the end. So I don't think we have time for a poll, but the next thing we wanted to do was look at the efficacy of these slides. So we used mouse models of ITP. Next slide. If you just look at the left corner there, the left figure, we used a model called a dose escalation mouse model, and we would give treatment at 2 days when the platelet count would drop to its nadir, and then see if we could get a rise in platelets. Next slide. And this is what we got. So whether we used iso-reduced or non-reduced IVIG, we always got an increase in platelets. So there wasn't any difference in efficacy in the ITP model. Next slide. So the next thing we want to do is investigate the efficacy in another model of autoimmunity that works with IVIG, and that's the rheumatoid arthritis mouse model. Next slide. We're going to go over these slides. No poll. Next. Anyway, this is an unusual model. It's a cool model, but you can read about it in the reference. Next slide. I'm just going to get to the data. Sorry, but he's waving goodbye. Next. Just look at the left side. We do clinical scores. The highest clinical score that we could get is 12, but this is a serum transfer. So these mice develop arthritis, but you can take their serum and you can inject that into any mouse and they will develop arthritis. And that's what we did here. And basically the bottom line here is that there's no difference between iso-reduced or non-reduced in amelioration of the arthritis, which is the yellow and the blue lines there you see below the non-reduced without the treatment. Next slide. And we did this in 2 different mice, got the same results, so it seems to work as well as non-reduced. Next. Okay, so sorry I had to go through those quickly, but next slide. So just simply, I will go through these. So titers of anti-A and anti-B we've determined are very low in Privigen. They're still there, but they're very low. Using an equivalent dose of up to 4 grams per kilo in the MMA, which I didn't show you that data. We never saw any hemolysis to be predicted. In other words, they never got above a phagocytic index of 5. If we use activated or inflammatory macrophages, M1 or M2, that didn't increase the phagocytosis to a significant level. So inflammatory macrophages, it doesn't matter. It's not going to cause an issue with the iso-reduced. And then the prediction, of course, is it would produce fewer hemolytic adverse events in patients requiring high-dose IVIG, but it also doesn't affect the efficacy. So the final thing here that we would conclude is that isogluten-reduced IVIG should have the same therapeutic efficacy, but with less hemolytic adverse events. And sorry if I went over. Thank you, everybody that works in my lab.
Thank you. Pardon me. Thank you very much. Thank you very much, Don. Last poll.
It's not too bad. Okay, the last poll is how relevant do you feel the evidence behind isogluten reduction is to your clinical practice? So most of you chose very relevant, and I guess we've done our job then. So I think that'll be it, and we'll go off to other questions if there's time. And I think the final remarks by David.
Yeah, we'll just do a couple of real quick ones, Don, if you don't mind. Here's one. This is a double or triple barreled. Many patients complain of fatigue post-IVIG. For replacement therapy specifically. How much of this could be due to subclinical hemolysis? Has it been looked at? Could iso-reduced decrease this? If so. And by extension, is this why fatigue is less common with SCIG subcutaneous?
That question might be more appropriate for Jacob, but I would say that I don't know if it's been studied much. Certainly IVIG-induced hemolysis has been shown in IVIG replacement therapy. Whether or not that's involved in fatigue, I wouldn't have a good answer for that. I mean, anything is possible. But if it is involved in the fatigue, IVIG hemolysis, and certainly I would think that iso-reduced IVIG would be beneficial.
Right. Any further comment, Jacob, on that?
Yeah, I mean, I think it's an interesting question. You know, like I said, we don't know how common or how severe hemolysis is with SCIG. I can tell you from our study, though, that we actually did not see any signal between the hemolyzers or the non-hemolyzers in terms of symptoms. Everybody had headaches. Everybody felt tired. So that didn't actually distinguish the severity.
Interesting.
So I think, I would guess that, a patient who gets tired after getting SCIG might be tired because of the work of actually administering the therapy or coming to get it.
Very interesting, and a very interesting question.